Hi, my name is Sergey Levine, and today I'm going to talk about deep model-based RL for real-world robotic control. So, as we all know, deep learning helps us handle unstructured environments, from image recognition to translation to speech recognition. And reinforcement learning provides a formula for behavior. In RL, we have an agent that makes decisions, and the world responds with consequences, observations, and rewards. So we might think that deep learning plus reinforcement learning could enable effective decision-making in unstructured settings. And in fact, we've seen that reinforcement learning works very well in a range of difficult situations, from playing video games to controlling robots in simulation, even to rudimentary real-world robotic tasks. So we might think that it could succeed in a range of real-world robotic problems that require generalization. However, the kinds of domains where deep learning methods have generalized are typically characterized by very large datasets and very large models that can train on those datasets for a long time, in vision, in speech recognition, and in NLP. In robotics, if we want to use RL, we're suddenly faced with a very different training recipe, where you have an active interaction loop, where the agent needs to interact with the world to collect its dataset each time it learns a new skill. If you have to collect your own dataset each time, then it might be impractical to have a dataset large enough to see meaningful generalization. So a very important question that we have to ask is, how can we generalize effectively without being able to train on large datasets? I think the answer is that we really can't. What we really need is a different way of thinking about robotic RL, where we have algorithms for scalable off-policy reinforcement learning and datasets that can be used to learn generalizable skills. This is fundamentally a multitask way to think about RL, where you have a machine that has collected a large dataset of past experience, and that past experience will be used to train for many epochs to learn a generalizable skill, and then occasionally go in and get a little bit more data if your particular skill demands it. One very effective way to imagine this working out is in the setting of model-based reinforcement learning, which of course is also something that fits with the theme of this workshop. In model-based reinforcement learning, you have an agent that collects a dataset of interaction from its past experience, which we can say consists of states, actions, and next state tuples. And then we're going to ask the question, what can we learn from past data that can be applied to many future tasks? Well, what about learning how the world works? If we can use this data to learn a predictive model that predicts the next thing that the agent will observe, given its current state in action, and then train this model for many epochs on diverse datasets, and then occasionally get more data if necessary, this powerful model will allow us to then perform a wide variety of tasks insofar as it can effectively predict real-world interactions. So the main idea is to learn a predictive model from diverse data and use this model to perform new tasks. To realize this idea, we need to actually develop effective deep model-based RL algorithms. So in today's talk, I'm going to discuss the basics of deep model-based RL. I'm going to talk about how we can extend this to deep model-based meta-reinforcement learning. And then I'll talk about how we can extend it to use image observations. But let's start with the basics. So here's our recipe from before. We're going to need to train a model, and this model takes as input the state and the action, and it predicts the distribution of our next states. And it'll be represented by a deep neural network because we're doing deep RL. So we'll denote it P subscript theta, and it's a distribution over S prime given SA, where theta denotes the parameters of the network. We'll train it with maximum likelihood, which means that we'll sample tuples from our dataset and maximize the likelihood of the next state given the current state in action. And then once we've trained this model, we can use it to do control. There are a number of ways to use a model to do control, but the simplest one, and the one we'll explore in all the methods that I'll discuss today, is to simply plan through the model. So there's no additional policy being learned, no additional value function, just a model which will be used to do control. Planning here is simply an optimization problem. It's a matter of choosing a sequence of actions, A1 through AH, that'll maximize the expected value of the reward, where the expectation is taken with respect to this model. So this is essentially planning. So you could imagine that your robot has a learned model. It's going to pick some sequence of actions, predict the total reward. Maybe it's 13.2, pick a different set, 23.4, pick a different set, 56.3, and then take the best one. An important detail is that you really want to replan every time, because if your model is not correct, you won't get quite the outcome you expected. So if you replan every time step, you'll be able to do a little bit better. An important question you have to ask is, which planning or optimization method should you use? And there are lots of options, from linear quadratic regulators to RRTs, PRMs, etc. Actually, in all the work that I'll discuss today, we're going to use a very simple method. We're going to use a derivative-free optimization technique called the cross-entropy method, or CEM. We actually introduced this idea to the world of deep model-based reinforcement learning roughly 3 years ago, mostly because we were too lazy to code up anything more sophisticated. And unfortunately, the idea is stuck, so I really apologize for that. There are quite a few papers that use CEM these days for model-based deep RL. It's not by any means the best method, it's just the method we picked because it was the easiest for us to implement. And I'm sure there are many better choices, but it's actually going to be good enough for many of the things I'll discuss. Now, when we started working on deep model-based reinforcement learning in late 2017, at the time, deep model-based RL really didn't work. So this is an experiment that we did. Here, we're going to be controlling the half-cheetah robot, and the little orange bit shows what happens when you run model-based reinforcement learning using the recipe I discussed on the previous slide. What the red part shows is if you then take the result of model-based RL and fine-tune with model-free RL. So pure model-based RL is very efficient. It takes about 10 minutes of real time, and then it basically plateaus. It won't improve anymore from there. At that point, it gets about 500 reward on this task. If you then fine-tune with model-free RL for the equivalent of about 10 days, of course, the simulator is faster than real time, so it goes a bit quicker than that, but if it was real time, it would be 10 days. You get to about 5,000 reward, 10 times better. Here's what 500 reward looks like. It's not terrible. The cheetah actually does manage to make some forward progress. But here's 5,000 reward. So something is clearly missing. Now, we were actually pretty happy with these results back in 2017 and 2018 because this was still much better than any previous deep model-based RL method. But there's clearly still a long ways to go. So why is there this performance gap? Well, one of the reasons is that when you're learning from limited data sets, you need to have a model class that doesn't overfit over here when it has a very limited amount of data, but still has high enough capacity over here. If you start with high capacity right away, then you'll overfit catastrophically and fail. If you start with low capacity, you'll make progress, but then you'll plateau. So one of the ways that we can understand this, the reason for this plateauing and this overfitting problem is if you think about what actually happens when you fit a model. When you fit a model to limited data, you're going to make mistakes. So imagine this cartoon represents the reward on the y-axis and the trajectory on the x-axis. You have some fit, your fit goes through the data very well, but in some places it'll make mistakes, often due to overfitting. When you then optimize your reward with respect to your actions, you'll go to exactly those places where the model makes the largest mistake in the positive direction. And this can be catastrophic for the performance of model-based RL methods, and this is a big part of why they didn't work so well for a long time. So perhaps uncertainty estimation can help. Maybe instead of just estimating the model, we can provide uncertainty estimates, and then with these uncertainty methods, we'll basically avoid trying to exploit the model. To understand why uncertainty estimates allow you to avoid exploitation, think about this example. You have to walk to the edge of a cliff. If you believe your model is confident and correct, you'll walk right to the edge. But if your model has some uncertainty interval, then you'll actually be more conservative. You won't walk all the way to the edge of the cliff because there's some chance that you'll fall off. So the expected reward under high variance prediction is actually very low, even though the mean might be the same. So how can we build uncertainty-aware models? Well, the difficulty is that it's not enough to just produce a distribution over the next state. You really have to estimate model uncertainty. Model uncertainty means that the model is certain about the data, but we are not certain about the model. Conventional discriminative training won't give you this. So what you need is some more Bayesian approach. Usually we estimate the maximum a posterior parameters given our data, but here, if we want model uncertainty, we need to estimate the uncertainty over the parameters of the model given the data set. And the entropy of that posterior will tell us how certain we are about the model. And then we'll predict by integrating out those parameters. There are many ways to do Bayesian deep learning, but a very simple technique that actually works well in model-based RL, which we figured out could be effective right around 2018 for these problems, is to use what's called Bootstrap ensembles. Instead of training just one model, we actually train a collection of models, and then we measure their agreement or disagreement as a measure of certainty. Formally, your posterior parameters is given by a collection of point estimates, basically Dirac deltas at the parameter vectors of the models in the ensemble. So if you train multiple models, and then if you want to integrate out the parameters, you simply average those models together. How do you train? Well, the main idea is you need to generate independent data sets to get independent models. And one of the ways you can do this is you can resample your data set with replacement. This is the standard Bootstrap method. It turns out that in deep learning, it's actually even simpler than that, because you can use a fairly small number of bootstraps in your ensemble to get decent uncertainty estimates, and resampling with replacement is usually not even necessary because SGD and random initialization already makes the model sufficiently independent. So we certainly didn't come up with a Bootstrap, and we didn't come up with the idea of using Bayesian nets, but we did attempt to use it for deep model-based RL, and that turned out to lead to very large improvements. So here are a few benchmark tasks: cartpole, half cheetah, reacher, pusher. You saw the half cheetah before. Here are the results for using the Bootstrap ensemble with model-based RL, using the same recipe as before. The blue line here shows this proposed method called PETS, and I'll draw your attention to the half cheetah task. We saw before that model-based training reached a reward of 500, while subsequent model-free fine-tuning reached a reward of 5,000 after the equivalent of about 10 days of training. Here, the model-based method with this ensemble reaches the same performance, actually a little bit higher, around 6,000, after 40,000 steps, which corresponds to about 10 minutes of training, drastically faster than the model-free approach from before. So simply modeling uncertainty, even in this crude way using ensembles, makes model-based RL work much, much better. But now we can ask another question. So far we saw that model-based RL can be more efficient, but are there other benefits? When should we prefer model-based RL over model-free RL? Well, on narrow tasks, where you can afford to collect a dataset for your specific task, model-free RL tends to do very well. So I'll discuss some experiments by my student Anusha Nagabandi, and these experiments study a pretty complex high-dimensional task. It's a dexterous manipulation task where you have to hold a pencil and use it to draw digits. Model-free RL methods, when they're asked to draw a single digit, here we're comparing SAC and natural policy gradient, which is very much like TRPO, you can see that everyone reaches maximum performance. The model-based method shown in green gets there much faster, but the final performance is the same for everybody. But if you have a broad and diverse range of tasks, model-based RL has a big advantage. So if you now ask this hand to draw many different digits, now you'll see that the model-based RL method over here still reaches maximum performance very, very quickly, but the model-free methods actually struggle to reach the same level of performance, even with drastically larger numbers of data points. And this agrees with our initial hypothesis that if we want this multitask setting, maybe model-based RL is a really good option. Another setting where we might prefer model-based RL is if we want to transfer the same dynamics model to perform multiple different tasks. So in this experiment, what Anusha did is she trained a model for the task of rotating these two Baoding balls. It's a kind of a hand exercise, a dexterity exercise. And then she showed that the same model could be used without any additional training to rotate the balls in the opposite direction or to reposition them to desired positions in the palm. Crucially, for these two tasks at the bottom, no additional training was done. The same exact model trained for the task at the top could perform the tasks at the bottom simply by being provided with a different reward function. Anusha also demonstrated that you could use this model-based RL method to train a very complex dexterous manipulation task directly in the real world. So what you're seeing here is a shadow hand learning to perform the real-world version of this Baoding balls task entirely from scratch. There's no simulation, there's no pre-training, all data is collected directly on the robot with real-world trials, and this is doing pure model-based RL. After about 1.5 hours, it can occasionally make a full turn with both balls, and for 4 hours, it can do this task very, very consistently. And again, this is entirely trained in the real world. For those of you that have seen some of the sim-to-real transfer results from OpenAI, those results required the equivalent of about 150 years of training and simulation. This requires 4 years in the real world and can manipulate two objects at the same time. All right, but now let's talk a little bit about meta-learning. What if model-based RL doesn't work? What if there's some unexpected change that causes your model to fail? For example, for this ant robot, what if one of the legs breaks? Now your model that was trained for 4 functional legs will simply not be able to walk any longer. Here's another example. This half-cheetah robot is trying to run across floating platforms, and when it steps on platforms of unfamiliar buoyancy, it flips over. So what we can do is we can update our model. We can observe the next state, and we can actually train our model a little bit more on that next state and improve in the hopes of adapting to these perturbations. However, this is very, very hard because neural nets don't adapt well from just a single sample. We can address this issue by using meta-learning. So the idea in meta-learning is that instead of training the model to be good on our data, we'll train it to improve from our data. So in particular, we can sample maybe 2 time steps, and we can train our model so that it does well on the second time step after being updated on the first. So notice that our objective now is to maximize the log probability under theta I, where theta I is obtained by taking a gradient step on theta using the first time step. Now in reality, we wouldn't do this with just 2 time steps. We would actually train on k time steps and then try to do well on the next k. This is a basic meta-learning method inspired by MAML, and if we use this meta-learning method to learn to adapt, then when the ant's leg breaks, the model adapts almost immediately. The same thing with walking on these floating piers. When the cheetah steps onto a different floating platform, the model instantaneously adapts in just a few time steps, and the robot actually succeeds at the task. In fact, we can use this method in the real world. So here, Anusha applied this to the Velociroach robot developed in Professor Fearing's lab. It's a hexapodal robot, and we're going to make it walk on different terrains and on different slopes. So for training, we simply collect data walking on different terrains and use this for meta-training. This is all of the data that's seen during meta-training, just these 3 terrains. And then we're going to test it on other conditions. First, we'll amputate one leg. Here, the robot is trying to walk down the center line, shown in yellow. On the left, you can see standard model-based RL. On the middle, naive adaptation. And on the right, you can see our meta-learn method. Despite losing a leg, it adapts very quickly and manages to stay along the center line. We can also adapt to walking on a slippery upward slope. Again, these slopes were not seen during training, and you can see again that gerbil, which is the meta-learning method, manages to stay closest to the center line. We simulated a sensor miscalibration by rotating the shell, and again, the robot was able to quickly adapt to this miscalibration and succeed at the task. So model-based meta-RL does actually work in the real world. We've also applied model-based meta-RL in a more recent paper to enabling quadrotors to control suspended payloads. So here we're going to take a visual servoing approach. We're going to specify the desired path for the payload, not for the quadrotor, just for the payload, in image space, and the quadrotor will have to use model-based RL to determine the commands to send to the rotors so that the payload follows the desired trajectory. Crucially, the robot doesn't know the length of the tether or the weight of the payload in advance, so it has to adapt to it using a meta-learn model. Here's a simple experiment. We suspended an unknown payload from an unknown tether, and we're going to ask the model to adapt. You can see that initially it deviates more from the desired trajectory, but over time, the inferred latent dynamics converge to the correct posterior, and the robot is able to closely track the desired trajectory. That's just a little warm-up. What we'll do next is we'll actually task it with picking up and dropping payloads. So first, we have a little magnetic gripper. The robot doesn't know the weight of the gripper, so it has to adapt. So it does a little flight to adapt to the weight of the gripper. Then it's going to use the magnetic gripper to pick up the payload. When it picks up the payload, its dynamics change again, so it's going to fly around and adapt to the weight of the payload. And then we're going to perturb it by yanking the payload off, and it has to adapt again. So here you can see that model-based meta-RL can actually perform this pretty complex task. All right, now what about images? So far, all the examples I showed you use low-dimensional state for model-based RL, but we can apply the same exact recipe to images. If you do model-based RL with images, you're learning to predict the future. Here are some examples of a robotic manipulation task. Each row starts from the same initial image, but each column corresponds to a different set of actions. And you can see that for different actions, this predictive model now predicts images that the robot might see if it does those actions, including manipulation of objects. We can give it a task by selecting a point in the image and telling the robot where that point needs to go. And the robot will plan the path. Its model will predict what will result. Here it predicts that the stapler will move along with the hand. And when we actually run it in the real world, it in fact performs the task successfully. The basic model-based RL recipe is exactly the same as before. It's a combination of MPC, cross-entropy method for planning, and a predictive model, which in this case just happens to predict images. We can use a similar recipe to learn tool use. So here we're going to task the robot with tasks that involve moving multiple objects, and it will have to figure out, using its learned model, that it has to use a tool to move both objects together. We could constrain it so that it can't reach out for the object and has to actually pick up the tool. So here the robot's hand is not allowed to leave the green region, and it figures out that it has to pick up the tool and use that to scoop the blue object. And here is sort of an improvised tool use task where some students left some garbage on the table, and the robot figures out that in order to sweep the garbage to the edge of the bin, it has to pick up the bottle and use it as an improvised scoop. This model can also figure out when not to use tools. So if we tell it to move two objects together, it'll reach out, pick up the tool, and use the tool to move both objects. If we tell it to move a single object, then it knows that actually moving the object directly is much more expedient than trying to use the tool. Now, if we want to scale up this method to more diverse scenes, we'll have to do a bit better than collecting data with a single robot. In fact, beyond just collecting data for multiple tasks, we can collect data in different settings with different robots and different scenarios. In the same way that the ImageNet dataset was crucial to scale up image recognition, we believe that large datasets of robotic interaction are also crucial to scale up model-based RL. So to that end, we recently collected a very large dataset of robotic interaction data with vision-based model-based RL in mind that we call RoboNet. RoboNet consists of data from 7 different robots collected in multiple different labs with multiple different viewpoints and numerous objects. It includes a Sawyer, a Franca, a Baxter, a Widow X-arm, a wide variety of objects collected by 4 different institutions, hundreds of viewpoints, multiple different grippers, and so on. This dataset is available online for anyone to try, and we've already evaluated it with our model-based RL methods, and I encourage you to give it a shot. All right, so to conclude, I talked about deep model-based reinforcement learning, the basics, how we can combine it with meta learning, and how we can combine it with images. I'd like to thank all of my students who conducted much of this research, especially Anusha Nagabandi, who did much of the work that I presented, as well as many others. And I'd also like to thank you for listening.